Hello, this is Arman, and this is my Problem 1 video. So for 1A, the problem reads as such. A toy rocket is shot straight up into the air. After the rocket reaches its maximum height, it starts to fall, and after a few seconds, a parachute is employed for the rest of the trajectory. I separate into three different free body diagrams corresponding to the regions that I believe fit. So first, there's a force applied that is greater than the force of gravity that's being imposed on it. Therefore, we have a positive acceleration, which will cause the velocity to increase. Thus, eventually, the rocket runs out of the force applied, so it eventually is only being affected by force of gravity. So it starts to plateau as since there's negative acceleration, the rocket's velocity starts. We basically start to see a deacceleration, so the speed starts approaching zero, and eventually the acceleration starts overpowering the velocity essentially, so it starts becoming negative, and a parachute is um, deployed, so therefore we have a drag force that is being in place right here. So the rocket begins to move upwards with the positive velocity. Eventually, once it reaches its maximum height, where only the force of gravity is affecting it and canceling out until not really canceling out, but until the velocity cancels out because of the gravity, it reaches a velocity of zero, and then it starts to go down once the parachute is deployed. For 1B, the question says a skier starts at the top of an inclined hill at a certain angle, and then moves down the hill, speeding up at first, and then moving at a constant speed. After a while, the skier reaches a point where the hill's incline gradually flattens out to be horizontal. Fi- Finally, somewhere along the horizontal region, the skier comes to a stop. So I once again separated into two different regions. So at the beginning, we have a normal force that's canceling out the y component of the force of gravity. What's causing the skier to accelerate at the beginning is the force of gravity from the x component. Eventually, at the beginning, we're going to have some friction, but at the same time, on top of friction, we also have most likely a drag force, which is one of the main ways that it will cause it to reach a constant velocity, because otherwise it would require a change in incline, which is not mentioned in the problem. Eventually, once we do reach the bottom of the hill, we're gonna only have, since it's no longer an incline, we still have some velocity carrying over from the previous sections, because the velocity is increasing in region 1, but then being constant in region 2. So in region 3, there's going to be a deacceleration being applied, since the only force that's going on x-wise is the force of friction, and regarding the y component, the normal force and the force of gravity is canceling out. So eventually, we start accelerating, and then the speed begins to narrow out right about here, and then the deacceleration happens. It also is good to consider that you cannot make your line too steep, or otherwise this problem won't line up. So for the next problem, we have a ball hangs at the end of a string, and the ball is then given a large push, such that the ball moves in a vertical circular pattern, such that the speed is large at the bottom of the circle. So this is a good problem to consider in the terms of energy, where we have kinetic energy and potential energy from gravity, and also angular momentum and centripetal force causes it to always be at like the maximum difference. So we at the beginning we're gonna have a force of tension and a force of gravity that's canceling out the tension force, because it's not moving in a y component. It's solely moving sort of in an x component, which allows it to move kind of circularly if you view it in perspective of the ball. So the speed is the greatest at the bottom, because all of the potential energy is being converted into kinetic energy. So as it begins going up, the more and more kinetic energy is being converted to potential energy until it reaches its peak, where the conversion stops, and then it starts all the potential energy that's been converted turns into kinetic energy. It won't be basically self-sustainable, because it's slowly being converted to thermal energy at the same time and other forms of energy. So eventually it will stop moving, but if inferring no other forces are in play, and it's only being converted from kinetic to potential, it'll continue moving in the same pattern where the speed's always going to be the same at every point. Not The speed's going to be the same at the same point when viewing it at different times. But since there's thermal energy also because of force of friction, because just saying between the ball and the string from whatever's connecting the string to the center. There's going to be a friction force that's causing it to slow down as well as drag and all that. So eventually the ball will reach a stop, but the speed will always be greatest at the bottom, since that's when we're going to have the greatest amount of kinetic energy, and kinetic energy is equal to mv squared. So we'll have a 1/4 relationship between the gravity conversion. The next problem, we have a pendulum that's being employed, and the problem says a ball hangs at the end of a string. The ball is then given a small push such that the ball oscillates back and forth. From the word oscillates, we know that this has to be a pendulum, and pendulums period are only affected by the length and gravity. So the length of string. So no matter what, the pendulum's period will always remain the same. Now the pendulum speed is the greatest at the bottom due to the same logic of potential energy being converted to kinetic energy. Now, due to this, we have force of tension when this is inferring the ball is at rest. We have force of tension canceling out the force of gravity because it's just hanging there. Eventually, a force is applied, and the force begins to push it up. And then once it reaches its apex, it will basically have a velocity of zero. And then all that potential energy that's been stored by pushing it up is now going to be converted into kinetic energy. This will result in the pendulum that will basically oscillate back and forth until all the energy is basically converted to thermal energy or some other form of energy. Could be like sound or any other form. And also, you have to consider there's a drag on the ball, which is further producing thermal energy. So it's going to run out pretty quickly, unle- depending on how big the ball is and depending on other sorts of forms of factor. But inferring there's no force of friction and no drag force, it will just continue to oscillate back and forth the same apex, but eventually it'll begin to decrease in the like how far it goes, but the period will always remain the same that it takes for the pendulum to oscillate back and forth. Thank you for listening, and I hope you have a good day.